This lesson is an overview of containers and layout managers. In the previous lessons, we've been using a flow layout manager and a panel container to position and display components in a window. So you should have a fair idea of what's going on and how these guys work. But let me give you a quick rundown just to make sure we're on the same page. This is a very brief look at the purpose of a container. The most fundamental task of a container is to maintain a list of displayable components. A container is also a component, so it has a paint method and can display itself in a window. But the primary purpose of a container is to keep its own internal list of components and then put them on display when instructed to do so. It is the container's job to detect incoming events and pass them on to the correct component in its list. The container knows the size and position of each of its components when they are on display, so you move the mouse into a window of the container and click the mouse button. It's the container that gets the event. The container then figures out which of the components is being displayed at that position and passes the event on to it. If, for example, a container is displaying a group of buttons, only the button under the mouse pointer at the time of the click will get the event. If there is no component under the mouse pointer that has been enabled to receive events, then the event is simply discarded. A container is also a component, and like all components, it has a paint method. And also, like all components, the paint method is called with a graphics object when the time has come for the container component to display itself. It may have a background color or something else to display, and then it uses the window information passed to it in the graphics object to create a graphics object for each of its contained components. This new graphics object contains information on just the area of the window that component is responsible for painting, and each contained component is called, in turn, to paint its area. Another job of the container is to lay out the components in the window, but it hires someone else to do this job. The container also contains a layout manager object, and it's the layout manager that analyzes the list of components and figures out how big each one should be and where it should go. A container is never without a default layout manager. Whenever a container is constructed, it immediately constructs itself a layout manager, which it keeps on hand in case the occasion arises that it may need to position components for display. Different containers have different default layout managers. For example, the panel containers we've been using for examples in the preceding chapter uses the flow layout manager as its default. It's kind of an odd layout manager, but don't worry. We've got some that are a lot better. And you can always change the layout manager in a container. That's what we're going to be doing in the next few lessons. The upcoming examples demonstrate rules and options for different layout managers. Each layout manager has a standard set of methods that can be called to control it, but each one uses its own set of internal rules to size and position the components. Before the layout manager can begin any calculations, it must have the size information on each component. So it asks each component how big it is. It asks three questions. What is the smallest size you can be? What is the largest size you can be? And what is your best size? For some components, all three of these are the same. For some, only two will be the same. For example, a button may have a huge maximum size, larger than the screen, but its favorite and minimum sizes could be the same, and that could be determined by the size of the text it displays. And you know how the button can figure that out by looking at the font and the text for the font metrics object. Anyway, once all the sizes are determined, the layout is determined according to the rules inside the layout manager. It comes up with three pieces of size information for its container. What is the smallest size it can be? What is the largest size it can be? And what is its best size? Remember, the container is also a component, so it needs to be able to report these values to its container. Then comes the command from above, which tells your container how big it's actually going to be. You remember how the size thing worked. When the window was first being popped up, the top-level window generally let the container have its own way, and the top-level window sized itself to accommodate the container's favorite size. On the other hand, if you just resize the window with a mouse, this larger or smaller size is dictatorially sent to the container and to the layout manager, and the layout manager is instructed to make everything fit that new size. If you made the window too small, some of it will get chopped off, and you'll have to stretch the window out again to get it all back. But the layout manager did its best to follow the instructions. Okay, I know I've left out some details, but instead of filling in the blanks right now, let me just show you how to use the various layout managers to build windows. Then we'll go on to build a custom layout manager, and that should clear up your questions. The Border Layout Manager allows you to place 4 components around the edge of a window and place 1 component in the middle. It's quite easy to use. This example demonstrates the use of a Border Layout Manager to construct a window with 5 buttons. In this example, there is none of the code necessary to respond to the buttons. This is just an example to show you how they can be laid out in the window. Everything is done inside the Make Panel method. I hope you don't think that the name Make Panel has any special meaning. It's just a name I made up, and I use it in all of the examples just for the sake of consistency. In any of these programs, it could just as well be called Framis, Google, or Do Stuff. Here at the top is a button reference that's used to create all the buttons. We don't have to save it anywhere because with this program we don't care which button gets clicked. We create a panel object, and then we create the Border Layout Manager that we want the panel to use. The panel method setLayout is called to insert the new Layout Manager into the panel. This replaces the existing Layout Manager. The old Layout Manager no longer has a home or a purpose, so Java will destroy it and recycle the memory that was allocated to it. These 2 statements create a button object and add it to the panel for display. Now this is a different kind of add method than the one we've been using. With the Flow Layout Manager in the previous examples, we just called add with a component and no other information. That's because the Flow Layout Manager didn't require any sort of constraint information. It just took the components in the order that it got them and lined them up that way. The Border Layout Manager needs to be told where you want to put each component. And it can only hold 5 components. 1 against each edge of the window and 1 in the middle. As you can see, the 4 sides of the window are identified by their compass points. Anyway, running the program looks like this. You can see that the north and south components are used to fill the window completely horizontally, which means the east and west buttons are not able to reach the top or bottom of the window. If you change the size of the window, the buttons are instructed by the Layout Manager to change their size to make everything fit. The Border Layout Manager is actually more useful than it may seem at first because you don't have to fill in all the slots. Look at this. This example is just like the previous one, except there is nothing in the north and south positions. Only 3 buttons are added to the panel. You can do the same thing as this, but vertically by using only north, center, and south. And you can put spaces between the components by inserting vertical and horizontal gaps. These 2 methods Specify the size of the gaps. The default is 0, no gaps. In this example, a horizontal space of 10 pixels and a vertical space of 20 pixels will be inserted between the components. This lesson is about the Grid Layout Manager. You can use the Grid Layout Manager to lay out any number of components in a window, but you must specify the grid to hold a specific number of components. The grid is a fixed size, and the components are inserted into it left to right, then top to bottom. And all the components are displayed in the same size. Even with these constraints, this Layout Manager is actually quite useful. Here's how it works. This line creates a Grid Layout Manager. You can specify any layout you want, but this one is configured with 3 rows and 2 columns. The Grid Layout Manager is actually quite handy, and I use it quite often. The only real problem I have with it is I can never remember whether it's the number of rows or number of columns that come first in the constructor. I just looked it up to be sure, and it's rows that come first. The Grid Layout Manager is going to organize things into 3 rows, and each row will have 2 columns. The new Layout Manager is stored in the panel, and then we add 6 buttons, just enough to fill the grid. A Grid Layout Manager doesn't mind too much if you're a couple of components shy. It just leaves blanks where they would have gone. But if you add too many components, the Grid Layout Manager changes its dimensions to make room for them, and it never seems to change the dimensions in a way that you'd like. Now, these buttons all come up the same size in the window because this Layout Manager requires that all its components be the same size. Here, I'll show you. Here are the 6 buttons. These are all set to their preferred size, which is pretty small because the text of each button is so short. If they are different sizes, the grid layout adjusts all dimensions to accommodate the largest one. For example, this program is just like the previous example, except this last button, which has a label that's much larger than the others, so it'll require more space than the others. Here's how the grid handles that. As you can see, the Grid Layout Manager asked everyone what their minimum requirements were and then set all the grid dimensions to the size of the one required the most space. Oh, you can insert horizontal and vertical gaps between the components this way. These 2 lines of code establish a uniform separation distance of 20 pixels to be placed between all components, vertically and horizontally. This lesson is about the Grid Bag Layout Manager. Of all the layout managers, this one is the most complicated to use, but it could also be considered the most flexible. I'm going to try to not make any editorial comments about it. I'll just show you how it works. It's based on a grid, sort of like the Grid Layout Manager, but each column can be a different width. In a similar fashion, each row can be a different height. This means that you can have oblong-shaped openings in the grid in which you can stick components. The heights and widths of the grid openings are set according to weight values you assign to them. Also, a component can be inserted so that it covers more than one of these grid openings. Notice that this layout manager requires two import statements. That's because it requires the use of two classes. The grid bag layout class is the layout manager itself, and the grid bag constraints object is a convenience class used to set up the constraint values for each individual component as it is added to the container. We're going to be using a bunch of buttons for our components, so this is a general purpose reference to be used as a holding area while we work on each one. Here we construct a grid bag constraints object. We can use the same one over and over because its only purpose is to contain parameter values passed to a method. In a different design, this same thing could have been done by having each parameter listed on the method call, but there are 10 of them, and you normally want to just let most of them default anyway. If they were all listed on a method call, you'd have to code the default value for all of the ones you didn't even want to change. This line of code creates the new Grid Bag Layout Manager. Notice that you don't have to specify the size of the grid like we did with the Grid Layout Manager. This manager is smart enough to figure out how many cells it needs in its grid as components are added to it. Here, the Grid Bag Layout Manager is set as the layout manager for this panel. Now, this is the first button. The label on the button is set to indicate its location in the grid. Before we add it to the panel, it's necessary to set the constraints for it. So here, two of the parameters are set in the Grid Bag Constraints object. The values grid X and grid Y place the component in its location in the grid. Just like with the add method we used with the border layout manager, we use the add method that includes a constraints object. In that case, it was a specification of the position, north, south, so on. In this case, it's the whole set of constraints in the Grid Bag Constraints object. Of course, everything inside this object is set to the default values, except grid X and grid Y, which are set to indicate the button location. If we let that default for each button, they would all go in the same location in the grid. Anyway, we add a total of 6 buttons to the panel, each one in a different position, and each one's label showing what position it is. The program looks like this when it runs. You can see that the way we positioned the buttons there along the top and left side of the grid bag. If we resize this window, the buttons all remain with their existing constraints, size, and relative positions, and the whole grid bag tries to center itself in the window. The reason the buttons all stayed clustered together is because they all have the same weight value, and that weight value is 0 in both the X and Y directions. The value of the weight is a multiplier used as a factor in determining the space between the components and the sizing of the components. The grid bag layout is a very dynamic layout manager. Let's give the buttons a bit of weight so they'll spread out and try to fill the window. Now, this program is the same as the previous one, except we've added weight values to the button components. The weight values of each component are relative values among them, and the weights for all of the buttons that in this program are set to the same, so the sizing of their grids and thus the spacing of the buttons will all be the same. As you can see, this really looks no different from the previous example, but when you stretch the window, the weight of the buttons becomes apparent. As I'm sure you know, the same effect could have been achieved when the window was first opened by making a call to set size from inside the program. Another useful parameter is the one that instructs a component on how it should fill its grid. It can be instructed to always fill its grid vertically or horizontally, and in this example, The buttons are all set to fill their grids in both directions. The default is for no filling at all to be set or to take place, but we set every button in this example to both, which means when the grid expands, the buttons will expand to fit its space both vertically and horizontally. And we've set these weight values of the second buttons to 4, both horizontally and vertically. This will have a direct effect on the relative size of the grid as it expands. Here, I'll show you. Here you can see the buttons all expand to fill their sections of the grid, and you can see that the expansion is a little uneven. The button with the added weight is awarded more space. Let me expand it on out and you can get a better idea of the relationships. The weight value of this button is 4 horizontally, and so you can see it is about 4 times the size of the buttons with a weight of 1. Also, this same button has a vertical weight of 4, and that makes it about 4 times as high as the other buttons in the vertical position. When the window was small, this ratio was not so apparent because the buttons have a minimum size to contend with. I want to show you one more thing. A component can be spread across more than one grid square. Now, in this example, we create new grid bag constraints object for each button. This is to point out that if you use a grid bag constraint object, it has values set in it other than the default. To overcome this, you can either make certain that you set every value every time, or that you create a new constraints object for each button, as I've done here. For this button, we've set a couple of parameters we haven't seen before. The grid width and height values default to 1, but for this one, we set the height value to 3. This means this component will cover 3 cells. For this button, we set the width to 4, so the button will expand itself sideways to cover 4 cells. And this isn't all of the possible settings. You should experiment a little to see how it all works, and try the iPad X and iPad Y settings to insert space around the components. And there are other controls that will set components in different locations within their cells. This lesson is about a couple of new things. It introduces the Card Layout Manager, and it shows you an example of using more than one panel and more than one layout manager to construct a window. First, note that there is a declaration of a reference to a card layout and a panel located here at the top of the class. We're going to need to refer to both of these in the callback, so they are kept here so the callback method will have access to them. This MakePanel method constructs a panel and sets its background color. This is the color that will come through in all areas that we don't cover with other components. Remember that a panel is not only a container, but it's also a component, so it has such things as color settings. We're going to be using a border layout manager because we want to put one item at the top and another at the bottom. So 2 calls are made to add one component north and another one south. Now, the north component is actually another panel, and this is the one that uses the Card Layout Manager. The Card Layout Manager manages several components, but only displays one of them at a time. It sizes itself to the largest height and width that it will need to be able to display every component in its containers list. And this particular one is going to insert horizontal and vertical gaps of 10 pixels each around the component that displays. The first component added is a label that will display the word first. So we can easily tell when the Card Layout Manager switches from one to the other, each of the labels are given a different background color. Notice that the constraint parameter on the add method call is a character string. This is a name assigned to the component internally. In this example, we assign the names because it's required, but we don't do anything with them. On the label component and on other components that display text, it's possible to set the color of the text by calling set foreground. That was done for a couple of these labels to prevent the text from being swallowed by the background color. Altogether, 6 labels of various colors are added to the panel with the Card Layout Manager. The bottom half, the south half of the main panel, is to be a row of buttons that are to be used to manipulate the display of the Card Layout Manager. It starts out as a panel with a Flow Layout Manager. 4 buttons are added to the panel, and each one is labeled for the Card Layout Manager method that it will call, and each one is assigned this object as its action listener. This is the callback method called with every button click. The button labeled first causes a call to the Card Layout Manager's first method, making its first component become visible. There is one button that will switch the Layout Manager to the next component, one for the previous and one for the last. Notice that these calls to the Card Layout Manager methods that switch components require that the container be passed also as an argument. That's why both of them were declared at the top of this class, so we could find them from here in the callback. Now here again, I just grabbed the easiest colors I could find, the ones that already are defined in the color class, but it doesn't matter. I mean, even if I had spent a couple of hours working on it, it would still look kind of funky, you know. I don't have any taste. Anyway, the Card Layout Manager can flip through any number and any kind of components, even a collection of panels, and each one of those could be managing several components, and so on and so on. This lesson is about locating components in a window at specific locations and with a specific size. If you're the kind of person that greases your own car, then listen up. This is your lesson. It's a very simple thing to do, really. I'll start off with the simplest possible approach and then show you how to spiffy it up a bit. This Make Panel method creates a panel, and then, instead of replacing the default Layout Manager with another one, a null argument is passed to set layout, which simply removes the Layout Manager. Without a Layout Manager, all the sizing and positioning must be done explicitly, and that's what happens in this method. A button is created and has its size and positions set. The first 2 values are its X and Y positions, the last 2 are the width and height. The same things are done with the second button, and then with a third. Nothing moves. Everything stays the same size and in the same position. Because of the lack of a Layout Manager, it was necessary to set the size of the panel, because no size calculations are going to be made with a Layout Manager missing. The result looks like this. As you can see, everything is right where we put it. Doing it this way, there's nothing to prevent you from overlapping components and even placing them outside the display area. You can be very specific and get just exactly what you want. Another approach to getting your own way is to create your own Layout Manager. It's easy to do, and with your own layout manager you can make things work just exactly the way you want them to. Here's an example of a simple layout manager. It's one that I've used a few times. Now this is called the XY layout manager because you still have to specify the X and Y positions of the components, but the layout manager handles the window sizing and all the components are displayed in their preferred size. Notice that layout manager is actually an interface, not a class. That means that to create a layout manager, it's only a matter of implementing the required methods defined in this interface. Most layout managers keep an internal list of components, and these two methods are called to insert and delete members of the list. This layout manager doesn't keep a list, so these methods don't do anything. This method is called to determine the minimum size of the window after it's laid out. This layout manager doesn't ever move any of the components, so it just figures out the smallest possible window size that can display all of them. This call to get component count returns a count of the number of components in the window. This loop executes once for each component in the window. The dimension object returned from this method contains the height and width of the component. The location of each object is retrieved in the form of a point object, which holds the X and Y values. Using these values, it's possible for this loop to determine the rightmost and bottommost edges of the contained components. With that information, it's easy to determine the height of the window required to display them, and those values are returned in the form of a dimension object. Now, in this layout manager, the preferred size is the same as the minimum size, so the preferred layout size method simply returns the results from the minimum layout size method. If we wanted, we could add something to the preferred layout size to allow for borders around the edges, but this is a simple layout manager and it only has one size. Now this method is called to perform the actual laying out of the components. The layout manager only works with this minimum size, so there's no need to even check if the container's window is large enough or too large or whatever. This loop sets each component to its preferred size. Other things could be done. For example, things could be made a bit more fancy by checking for the size of the window of the container and adjusting the positions of the components so there's a little margin all the way around. Anyway, as simple as it is, it's a fully operational layout manager. Here's a program that uses it. A new XY layout manager is constructed and inserted into the panel to be the layout manager for this panel. 4 buttons and 1 label are constructed inside the method, assigned an XY location, and added to the panel. Note that no information about the size of the window is specified anywhere. If the layout manager does its job, not only will all the components be displayed at their specified locations, they will all be allowed to assume their preferred sizes, and the window should be sized so they all just exactly fit. Looking at this, it would probably have been a good idea to add the code to the layout manager to insert a little margin around the components, but you get the idea. That's all we're going to do with layout managers in this course. There are quite a few more, but the ones that are shown here are the ones that first appeared in Java and are somewhat representative of the others. But you know how to use them, and you can look them up in the documentation and try them for yourself.